As you settle into the gentle safety of your bed tonight, perhaps aware of the subtle sounds of wind against your window or the distant rumble of a passing storm, take a moment to appreciate that you're nestled within one of the universe's most magnificent and dynamic systems, Earth's atmosphere. This invisible ocean of air that surrounds our planet is never truly still, never truly at rest. It moves in patterns both delicate and powerful, creating the weather that shapes every day of your life, and occasionally, the extreme weather events that remind us of the awesome creative forces at work in our sky. Tonight, we'll explore not the destructive power of extreme weather, but rather its profound beauty as nature's grandest theater, where physics becomes visible poetry, where the fundamental forces of our planet express themselves in displays so spectacular they can humble and inspire in equal measure. These are not chaotic events, but rather the elegant results of physical laws playing out on a scale that transforms our atmosphere into a stage where temperature, pressure, and moisture perform in combinations that can create both gentle morning mist and the spiral majesty of hurricanes. The atmosphere above you right now is a living system, a fluid ocean of gases in constant motion, driven by the sun's energy and Earth's rotation. Even in the calmest weather, this aerial ocean is flowing, circulating, mixing, and redistributing energy from the warm equator toward the cooler poles. The air molecules around you have traveled incredible distances. Some may have circulated around the globe multiple times, carrying with them the thermal memories of tropical seas, Arctic ice sheets, and vast continental land masses. Extreme weather emerges when this atmospheric system encounters conditions that push it beyond its normal patterns of gentle circulation. But even in extremity, these events follow beautiful physical principles that transform chaos into organized power. A thunderstorm, for instance, is not a random explosion of atmospheric violence, but rather nature's elegant solution to correcting an imbalance of temperature and moisture in the atmosphere. The towering cumulonimbus clouds that create these storms are actually atmospheric elevators, lifting warm, moist air from the surface high into the cool upper atmosphere in a process that can release energy equivalent to hundreds of atomic bombs, yet does so with a precision and beauty that speaks to the underlying order within apparent chaos. Consider the physics behind a simple raindrop's journey from cloud to earth. Each droplet begins as invisible water vapor that is evaporated from oceans, lakes, or rivers, carried aloft by ascending air currents until it reaches altitudes where cooling temperatures cause it to condense around microscopic particles of dust or pollen. In gentle weather, this process creates the soft clouds that drift peacefully across your daytime sky. But when atmospheric conditions are more dynamic, when warm, moist air encounters dramatic temperature differences or wind shear, these same physical processes can create towering storm systems that stretch from near the Earth's surface to the very edge of space. The spiral beauty of hurricanes emerges from the Coriolis effect, the same physical principle that influences the rotation of water draining from your bathtub, but scaled up to continental proportions. As warm, moist air rises from tropical oceans and cooler air rushes in to replace it, the rotation of the Earth gently deflects these air currents into the characteristic spiral pattern that, seen from space, resembles a vast atmospheric rose blooming over the ocean's surface. The eye of the hurricane, that famous circle of calm at the storm's center, represents one of nature's most elegant solutions to managing the enormous forces at play, creating a zone of stability within the swirling energy that allows the entire system to maintain its coherent structure. Tornadoes, those dramatic columns of rotating air that can seem so terrifying from ground level, are actually the atmosphere's way of resolving conflicts between air masses of different temperatures and humidity levels. When warm, moist air from the south encounters cool, dry air from the north, and when winds at different altitudes blow in different directions, the atmosphere essentially ties itself into knots. Beautiful, powerful knots that manifest as the distinctive funnel shapes that have fascinated humans for generations. From a meteorological perspective, a tornado is simply air following the path of least resistance as it seeks to equalize pressure and temperature differences, creating in the process one of nature's most graceful expressions of rotational dynamics. Even the gentlest aspects of your daily weather emerge from the same fundamental processes that create extreme events. The morning dew on your garden plants forms through the identical physics that create the massive cloud systems of hurricanes, water vapor condensing as temperatures cool. The gentle breeze that might rustle your curtains operates according to the same pressure gradients that drive the jet stream winds that can reach speeds of over 200 miles per hour. The comfortable temperature in your bedroom exists within the same atmospheric system that can generate both the furnace-like heat of desert summers and the profound cold of polar winters. This perspective transforms how we understand extreme weather, not as aberrations or attacks from nature, but as the normal expression of our planet's atmospheric system when conditions align to create events of unusual magnitude and beauty. These phenomena represent the same planet that gives us gentle spring rains and comfortable autumn breezes. They're simply the atmosphere expressing its full range of capabilities, much like an orchestra that can play both whispered lullabies and triumphant symphonies. Tonight, as you rest safely indoors, you can appreciate that you exist within this magnificent atmospheric theater, protected and sustained by the same system that creates both the gentle circulation of air in your room and the awesome spectacles of extreme weather that remind us of our planet's dynamic nature. The air you breathe, the comfortable temperature that surrounds you, and the stable pressure that allows your body to function normally are all gifts from this same atmospheric ocean that occasionally expresses itself in more dramatic ways. As you drift towards sleep, let yourself feel gratitude for the invisible protection of Earth's atmosphere. This thin shell of gases that shields you from space, regulates temperature, distributes moisture, and creates the weather patterns that make life possible, while occasionally staging some of the most beautiful and powerful displays in the natural world. The dance of storm formation. Tonight, as you rest in the calm sanctuary of your bedroom, let your mind drift to the graceful choreography that unfolds in Earth's atmosphere when conditions align to create the magnificent spectacle of storm formation. Far from being chaotic or violent events, storms represent some of nature's most elegant solutions to atmospheric imbalances. Vast aerial ballets where air masses perform intricate dances guided by the fundamental forces of physics, creating displays of organized power that can stretch across entire continents. Imagine the birth of a thunderstorm, beginning with something as gentle as the morning sun warming the earth beneath your feet. As solar energy heats the ground, it creates invisible columns of rising warm air called thermals, the same updrafts that allow birds to soar effortlessly through summer skies. These rising air currents carry with them moisture evaporated from oceans, lakes, and rivers, lifting countless water molecules high into the cooler regions of the atmosphere, where a remarkable transformation begins to unfold. As this warm, moisture-laden air ascends, it encounters the decreasing pressure and temperature of higher altitudes. The water vapor it carries begins to condense around microscopic particles of dust, salt, or pollen, forming the tiny droplets that create the first wisps of cumulus clouds, those cotton ball formations that drift peacefully across fair weather skies. In gentle conditions, this process creates the serene cloudscapes that bring beauty to your afternoon walks. But when atmospheric conditions are more dynamic, when temperature differences are more pronounced, and winds are more energetic, this same process becomes the foundation for nature's most spectacular atmospheric architecture. The transformation from peaceful cumulus to towering cumulonimbus, those cloud mountains that can reach heights of 60,000 feet, unfolds like time-lapse footage of a growing crystal. As more warm air rises and more moisture condenses, the cloud releases latent heat energy, warming the air around it and creating even stronger updrafts. This creates a feedback loop where the cloud literally feeds itself, growing taller and more powerful with each cycle of rising air and condensing moisture. What began as gentle thermals becomes a vertical river of air flowing upward at speeds that can exceed 100 miles per hour. Within these towering cloud structures, a fascinating dance of ice and water unfolds in the sub-freezing temperatures of high altitudes. Supercooled water droplets, liquid water existing below freezing temperature, collide and merge with ice crystals, creating the hailstones that will eventually fall to Earth. The constant circulation within the storm cloud carries these growing ice pellets up and down through temperature zones, adding layer upon layer of ice like an atmospheric pearl-making process. Some hailstones may travel this vertical journey dozens of times before finally becoming too heavy for the updrafts to carry, falling to Earth as evidence of the remarkable forces at work miles above your head. The electrical displays we call lightning emerge from this same vertical motion within storm clouds. As ice crystals and water droplets collide and separate within the turbulent cloud interior, they create electrical charges that accumulate until the atmosphere can no longer contain them. Lightning represents the atmosphere's way of equalizing these electrical imbalances, creating channels of superheated air that can reach temperatures of 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. Yet this seemingly violent process follows precise physical laws, creating the branching patterns we see because electricity naturally follows the path of least resistance through varying air densities. The thunder that follows lightning tells its own story of atmospheric physics. The instantaneous heating of air by lightning creates a shock wave that propagates outward at the speed of sound, creating the rumbling symphony we hear as thunder. The rolling, continuous nature of thunder comes from the zigzag path of lightning channels. Each segment creates its own sonic boom that reaches your ears at slightly different times, creating the extended rumble that can last for several seconds as the sound waves bounce and echo through the landscape. When storm systems encounter the additional complexity of wind shear, layers of air moving at different speeds and directions, they can develop the rotating characteristics that create tornadoes. Picture this as the atmosphere learning to spin, with horizontal tubes of rotating air being tilted vertical by powerful updrafts, creating the distinctive funnel clouds that touch down to Earth. The mesmerizing rotation of tornadoes follows the same principles that govern the spinning of figure skaters. As the column of air contracts horizontally, conservation of angular momentum causes it to spin faster, creating the intense vortex that can generate winds exceeding 300 miles per hour. On larger scales, when vast regions of warm, moist air encounter cooler, drier air masses, the resulting weather fronts create some of nature's most dramatic atmospheric theaters. A cold front, where dense, cool air wedges underneath warmer air, can create a wall of storms stretching for hundreds of miles. These squall lines represent the atmosphere's organized attempt to mix air masses of different temperatures and humidity levels, creating temporary boundaries where the contrasting air masses meet and interact in spectacular fashion. The formation of hurricanes requires an even more delicate balance of conditions. Warm ocean waters providing energy, low wind shear allowing the system to organize, and the Coriolis effect from Earth's rotation providing the initial spin that will eventually create the characteristic spiral structure. These tropical cyclones begin as gentle areas of low pressure over warm ocean waters. But when conditions are right, they undergo a remarkable transformation, organizing themselves into some of the most symmetrical and powerful storm systems on Earth. The eye of a hurricane represents one of meteorology's most beautiful paradoxes, a zone of relative calm at the center of incredible energy. This circular region of clear skies and light winds forms because the intense rotation of the storm creates a centrifugal force that pushes air outward, leaving the center relatively still. Pilots who have flown through hurricane eyes describe an almost surreal experience of sudden calm and brilliant sunshine, surrounded by towering walls of clouds that stretch as far as the eye can see. Tonight, as you rest safely indoors, you can appreciate that these same atmospheric processes that create extreme weather also generate the gentle breezes that cool your summer evenings, the refreshing rains that water your garden, and the comfortable air circulation that maintains the pleasant environment of your bedroom. The forces that can create magnificent storm systems are the same ones that regulate Earth's climate, distribute moisture around the globe, and maintain the atmospheric conditions that make life possible on our planet. As you drift toward sleep, let yourself marvel at the elegant physics that govern our atmosphere, where temperature differences, pressure gradients, and moisture content combine in countless ways to create weather patterns ranging from gentle morning mist to the awesome spectacle of nature's most powerful storms. The poetry of wind and pressure. As you settle deeper into the comfort of your bed tonight, perhaps feeling the subtle movement of air from your heating or cooling system, take a moment to contemplate the invisible rivers of air that flow continuously around our planet. The winds that carry stories of distant places, regulate our climate, and occasionally express themselves with such power that they reshape landscapes and remind us of the dynamic forces that surround us always. Wind is nothing more than air in motion, yet in that simple movement lies some of the most beautiful physics and poetry our atmosphere has to offer. The gentle breeze you might feel through your window right now began its journey somewhere else entirely, perhaps over a sun-warmed field hundreds of miles away, or above an ocean where temperature differences between water and sky set air masses in motion. Every breath of wind carries within it the thermal memory of the places it has traveled, the pressure systems it has navigated, and the temperature gradients that gave it birth. What you experience as a pleasant evening breeze is actually part of Earth's vast atmospheric circulation system, constantly working to balance temperature and pressure differences across our planet's surface. The fundamental principle behind all wind movement is elegantly simple. Air flows from areas of high pressure toward areas of low pressure, like water flowing downhill. But Earth's rotation adds a beautiful complexity to this basic pattern through the Coriolis effect, which gently curves the path of moving air masses. This subtle deflection creates the large-scale circulation patterns that govern our planet's weather. The trade winds that blow steadily across tropical oceans, the westerlies that bring weather systems across temperate continents, and the jet streams that race through the upper atmosphere like aerial rivers carrying weather patterns around the globe. The jet stream, that high-altitude river of air that flows at speeds up to 250 miles per hour, represents one of nature's most elegant solutions to planetary temperature regulation. Located where warm tropical air meets cold polar air, these fast-moving streams of wind meander around the globe like atmospheric serpents, carrying weather systems from west to east and creating the familiar pattern of high and low pressure systems that meteorologists track on weather maps. When jet streams develop large meanders, they can create blocking patterns that lead to extended periods of unusual weather, prolonged heat waves, persistent cold spells, or stationary storm systems that can produce extreme rainfall over localized areas. At ground level, the interaction between pressure systems creates the wind patterns that shape your daily weather experience. High-pressure systems, also called anticyclones, represent areas where cool, dense air is sinking toward Earth's surface, creating regions of generally stable weather with clear skies and gentle breezes that spiral outward clockwise in the northern hemisphere. Low-pressure systems, or cyclones, form where warm air is rising, creating areas of instability where winds spiral inward counterclockwise, often bringing clouds, precipitation, and more dynamic weather conditions. When these pressure systems are particularly strong, or when they encounter geographical features that concentrate or channel airflow, winds can reach extraordinary speeds that transform them into some of nature's most powerful phenomena. The Santa Ana winds of Southern California occur when high pressure over the Great Basin creates strong, dry winds that accelerate as they flow through mountain passes and canyons, creating the hot, desiccating conditions that can fan wildfires and create an almost ethereal atmosphere where visibility extends for hundreds of miles and the normal humidity of coastal areas temporarily disappears. In mountainous regions, the interaction between wind and topography creates some of the most fascinating examples of atmospheric dynamics. Chinook winds, also known as Fein winds, form when moist air encounters mountain barriers, forcing it upward where it cools and releases its moisture as precipitation on the windward side. As this now dry air descends the leeward slopes, it compresses and warms rapidly, creating dramatic temperature increases that can melt snow and ice with remarkable speed. These warm, dry winds can raise temperatures by 40 degrees Fahrenheit in just a few hours, creating temporary oases of spring-like warmth in the middle of winter. The most extreme expressions of wind power occur in tornado-producing supercells and hurricane systems, where specific combinations of atmospheric conditions create rotating wind patterns of incredible intensity and beauty. The mesocyclone rotation in supercell thunderstorms begins with horizontal wind shear, differences in wind speed and direction at various altitudes, which creates horizontal tubes of rotating air. When powerful updrafts tilt these horizontal rotations into vertical ones, they create the spectacular rotating updrafts that can eventually produce tornadoes. Tornadoes represent wind patterns so intense they seem to defy comprehension, yet they follow precise physical principles. The characteristic funnel shape results from conservation of angular momentum, the same principle that causes figure skaters to spin faster when they pull their arms closer to their body. As air spirals inward toward the low-pressure center of the vortex, it accelerates dramatically, creating wind speeds that can exceed 300 miles per hour in the most powerful tornadoes. The visible funnel we see forms when the low pressure within the vortex causes water vapor to condense, making the otherwise invisible rotating air column visible as a ghostly tube connecting Earth to sky. Hurricane winds represent organized rotation on an even grander scale, with entire storm systems hundreds of miles in diameter rotating around a central eye with mathematical precision. These massive atmospheric whirlpools form when the Coriolis effect combines with the energy released by condensing water vapor over warm ocean surfaces, creating self-sustaining systems that can maintain their organization for weeks as they travel across ocean basins. The spiral bands of clouds and precipitation that characterize hurricanes from satellite images result from the interaction between the storm's circulation and the physics of condensation, creating some of the most geometrically beautiful patterns in nature. Even the pressure changes associated with extreme weather systems tell stories of atmospheric dynamics. The dramatic drop in barometric pressure that occurs as a strong low-pressure system approaches can be felt by sensitive individuals and animals, creating the subtle physical sensations that often precede significant weather changes. Some people report being able to sense approaching storms through changes in joint comfort or general well-being, responding to pressure variations so subtle they're barely detectable by instruments, but clearly perceptible to biological systems evolved to sense environmental changes. The sound of wind itself creates a natural symphony that ranges from the gentle whisper of light breezes through leaves to the profound roar of hurricane-force winds. This acoustic landscape emerges from the physics of air movement over and around objects, trees, buildings, mountains, creating vibrations and resonances that vary with wind speed and the shape of obstacles in the airflow. The eerie howling of strong winds results from air turbulence creating pressure waves in the audible frequency range, while the gentle rustling of leaves in light breezes represents the same acoustic principles operating at much lower intensities. The artistry of precipitation extremes. Tonight, as you rest comfortably in your dry, warm bedroom, perhaps listening to the gentle patter of rain against your window or the profound silence of a snow-covered landscape, let your mind wander to the extraordinary ways our atmosphere transforms invisible water vapor into the magnificent variety of precipitation that falls from the sky. From the delicate geometry of snowflakes to the stunning power of monsoon rains, from the gentle mist of morning drizzle to the dramatic deluge of tropical cloudbursts, precipitation represents some of nature's most beautiful artistry, where physics becomes sculpture, chemistry becomes poetry, and the simple molecule of water reveals its infinite capacity for creative expression. Every drop of rain that falls, every snowflake that dances through winter air, every hailstone that bounces on summer pavement began its journey as invisible water vapor rising from Earth's oceans, lakes, and rivers. This vapor carries within it the thermal energy of its source. Warm tropical seas, sun-heated lakes, or moisture exhaled by vast forests. As this water-laden air rises through the atmosphere, cooling as it ascends, it eventually reaches the altitude where temperature and pressure conditions cause the invisible vapor to transform back into visible droplets or ice crystals, beginning the miraculous process that will eventually return this water to Earth in forms both gentle and dramatic. The formation of raindrops reveals physics, poetry, and motion. Contrary to popular imagination, raindrops aren't teardrop-shaped as they fall. Air resistance sculpts them into shapes that change with their size, from nearly perfect spheres for small droplets to flattened hamburger bun shapes for larger drops. The largest raindrops, about 5 millimeters in diameter, represent the upper limit of what surface tension can hold together. Anything larger breaks apart during the fall, creating smaller drops that continue their journey to Earth with their own unique shapes and fall velocities. Cloud formation itself is a masterpiece of atmospheric physics, where microscopic processes create the vast, billowing structures that paint our skies. Within clouds, water droplets and ice crystals grow through collision and coalescence, tiny droplets bumping into each other and merging, or ice crystals attracting supercooled water droplets that freeze on contact. This process requires remarkable precision of temperature and humidity conditions, with slight variations determining whether a cloud will produce gentle mist, steady rain, or no precipitation at all. When atmospheric conditions align to create extreme precipitation events, the results can be breathtaking demonstrations of nature's capacity for both beauty and power. The record for the most rainfall in a single day, 71.8 inches, was set on the island of La Réunion during Cyclone Denise in 1966. To put this in perspective, this represents more than the average annual rainfall for many temperate regions, compressed into just 24 hours. Such extreme rainfall occurs when tropical cyclones encounter mountainous terrain that forces moisture-laden air upward rapidly, creating orographic lifting that wrings extraordinary amounts of water from the atmosphere in concentrated bursts. Monsoon systems represent precipitation extremes on a seasonal scale, where entire continental climate patterns revolve around dramatic shifts in wind direction and moisture content. The Indian monsoon, for example, brings 80% of the subcontinent's annual rainfall during just 4 months, transforming landscapes from desert-like dryness to verdant abundance. These seasonal deluges result from temperature differences between land and sea that create powerful circulation patterns, demonstrating how our planet's geography and the physics of differential heating can create predictable yet extreme weather patterns that affect billions of people. At the opposite extreme, some regions experience precipitation scarcity so profound it shapes every aspect of the local ecosystem and human adaptation. Chile's Atacama Desert, one of the driest places on Earth, receives an average of just 0.04 inches of rainfall per year, so little that some weather stations have never recorded measurable precipitation. This extreme aridity results from its position between 2 mountain ranges and its location in a stable, high-pressure zone, creating conditions where moisture-bearing air masses rarely penetrate and humidity levels can drop to nearly zero. Snow represents perhaps the most artistically diverse form of precipitation, where the simple process of ice crystal formation creates an infinite variety of shapes and structures. Each snowflake begins as a microscopic ice crystal, forming around a particle of dust or pollen in sub-freezing clouds. As it falls, the crystal grows by attracting water vapor that freezes onto its surface, with the exact temperature and humidity conditions determining the final shape. The famous assertion that no 2 snowflakes are identical reflects the countless variables, temperature, humidity, air currents, and microscopic dust particles that influence each crystal's unique growth pattern during its journey from cloud to ground. Extreme snowfall events create some of winter's most spectacular displays, where the accumulated precipitation can reshape entire landscapes overnight. The record single-storm snowfall of 189 inches fell on Mount Shasta, California, in February 1959, creating drifts that temporarily buried first-story windows and transformed the familiar topography into an alien wonderland of white. Such extreme snow events typically result from atmospheric rivers, narrow bands of moisture-rich air that can transport water vapor equivalent to 15 times the flow of the Colorado River, dumping extraordinary amounts of precipitation when they encounter mountainous terrain. Hail represents precipitation that has undergone multiple journeys through different temperature zones within storm clouds, creating ice spheres that can range from pea-sized to larger than baseballs. The largest hailstone ever recorded weighed nearly 2 pounds and measured over 8 inches in diameter, falling in Nebraska in 2003. These ice projectiles form when strong updrafts within thunderstorms repeatedly carry frozen droplets up into sub-freezing zones where they accumulate additional layers of ice, like atmospheric pearl-making processes that can continue for dozens of cycles before the hailstones finally become too heavy for the updrafts to support. Freezing rain creates perhaps the most beautiful yet treacherous precipitation phenomenon, where supercooled water droplets freeze instantly upon contact with surfaces, coating everything in a crystal-clear layer of ice. This occurs when warm air overrides a shallow layer of cold air at the surface, allowing raindrops to remain liquid until they encounter sub-freezing temperatures at ground level. The result can transform ordinary landscapes into crystalline wonderlands where every branch, leaf, and blade of grass becomes encased in perfect ice sculptures that catch and refract sunlight into rainbow prisms. The phenomenon of virga, precipitation that evaporates before reaching the ground, demonstrates the atmospheric processes that can create visible precipitation without measurable accumulation. These ethereal curtains of rain or snow that hang from clouds but disappear into thin air reveal the dynamic relationship between humidity, temperature, and altitude that determines whether atmospheric moisture will complete its journey from cloud to surface or return to vapor form during descent. Microbursts represent precipitation-related wind phenomena that can create some of the most dramatic localized weather events, where rapidly falling rain or hail creates downdrafts so powerful they can exceed 100 miles per hour when they hit the ground and spread outward. These invisible columns of descending air can create damage patterns that look like tornadoes but result from completely different atmospheric physics. The cooling effect of evaporating precipitation creating dense, rapidly sinking air that impacts the surface with tremendous force before radiating outward in all directions. The acoustic landscape of precipitation adds another dimension to extreme weather artistry. The gentle whisper of light rain on leaves differs dramatically from the thunderous roar of heavy downpours on hard surfaces, while hail creates its own percussion symphony as ice balls of varying sizes strike different materials. Snow falls in virtual silence, its crystalline structure absorbing sound waves and creating the muffled, peaceful acoustic environment that many find so calming during winter storms. Lightning-triggered precipitation represents one of the more fascinating connections between electrical and hydrological atmospheric processes. Some research suggests that electrical charges in storm clouds may influence ice crystal formation and droplet coalescence, meaning that the spectacular electrical displays we see as lightning may actually be helping to create the precipitation that falls from the same clouds. This potential connection between electromagnetic and precipitation processes reveals the interconnected nature of atmospheric phenomena. The temperature at which different types of precipitation form creates distinct seasonal patterns that define regional climates and ecosystems. The freezing level, The altitude at which temperature drops to 32 degrees Fahrenheit determines whether precipitation falls as rain or snow, and seasonal changes in this invisible atmospheric boundary help create the rhythm of seasons that governs everything from agriculture to wildlife migration patterns. Extreme precipitation events often create temporary waterfalls, rivers, and lakes in places where they don't normally exist, transforming familiar landscapes into alien water worlds. Desert regions that might see no measurable precipitation for years can suddenly experience flash floods when rare but intense rainfall events overwhelm the normally dry drainage systems. These temporary aquatic features demonstrate the power of precipitation to reshape topography and create ephemeral ecosystems that exist only during and immediately after extreme weather events. The chemistry of precipitation varies dramatically depending on its source and the atmospheric conditions it encounters during formation and descent. Rainwater in clean environments is naturally slightly acidic due to dissolved carbon dioxide, but precipitation can also carry salts from ocean spray, dust from distant deserts, or pollution from industrial areas, creating chemical signatures that tell stories about the air masses and geographic regions the water vapor encountered during its atmospheric journey.
Tonight, as you rest safely indoors, protected from whatever form of precipitation might be occurring outside your window, you can appreciate that the water cycle represents one of Earth's most elegant recycling systems. Every molecule of water that falls as precipitation has been circulating through this system for billions of years, having been part of ancient oceans, prehistoric clouds, and countless previous precipitation events. The rain, snow, or hail that might be falling tonight connects you to the vast hydrological processes that make life possible on our planet. The gentle or dramatic sounds of precipitation against your window or roof provide a natural soundtrack that reminds us of our connection to atmospheric processes that operate on scales ranging from individual water molecules to continental weather systems. Whether it's the barely perceptible mist that creates morning dew, or the thunderous downpour of a summer cloudburst, precipitation represents the atmosphere's artistic expression of the fundamental physical processes that transform invisible water vapor into the visible, tangible phenomena that nourish our planet and create some of nature's most beautiful and powerful displays. As you drift towards sleep, let yourself be soothed by the knowledge that precipitation, in all its forms, represents the atmosphere's gift to life on Earth. The process by which the energy of the sun lifts water from the oceans and redistributes it across continents, creating the fresh water that sustains ecosystems, fills reservoirs, and maintains the hydrological balance that makes our blue planet unique in the known universe. The harmony of atmospheric forces. As you settle into the final moments before sleep tonight, surrounded by the gentle stability of your comfortable room, take a moment to appreciate the extraordinary harmony that emerges when all of Earth's atmospheric forces work together to create the complex, beautiful, and sometimes extreme weather systems that define our planet's character. What we call extreme weather is not nature gone wrong, but rather the full expression of our atmosphere's remarkable capacity to transform simple physical principles, temperature differences, pressure gradients, moisture content, and planetary rotation, into symphonies of such complexity and beauty that they remind us of our place within a dynamic, living planetary system. Throughout our journey together, we've explored individual aspects of atmospheric extremes: the elegant formation of storms, the poetry of wind and pressure, the physics of temperature extremes, and the artistry of precipitation. But the true wonder of Earth's atmosphere lies in how these forces interact,
creating integrated systems where every element influences every other element in cascading patterns of cause and effect that can span continents and to persist for months or even years. Consider how the jet stream, that high-altitude river of air we explored earlier, connects local weather patterns to global atmospheric circulation. A small change in sea surface temperatures in the tropical Pacific Ocean can alter jet stream patterns, which in turn can redirect storm tracks across North America, influence the duration of heat waves in Europe, and affect monsoon patterns in Asia. This interconnectedness reveals that extreme weather events are not isolated phenomena, but expressions of planetary-scale atmospheric dynamics, where distant causes can create local effects through chains of atmospheric influence that circle the globe.
The seasonal rhythms that govern extreme weather patterns demonstrate the beautiful predictability that emerges from cosmic mechanics. Earth's 23.5-degree axial tilt creates the seasonal cycle that drives monsoons, determines hurricane seasons, and establishes the annual temperature extremes that define regional climates. Yet, within this predictable framework, countless variables create the specific weather patterns that make each season, each storm, each extreme event unique. This combination of cosmic predictability and atmospheric chaos creates the rich, varied climate tapestry that makes Earth such a dynamically interesting planet. Climate oscillations like El Niño and La Niña reveal how the ocean and atmosphere work together as a coupled system, where changes in sea surface temperatures can reorganize global weather patterns for years at a time. During El Niño events, the warming of tropical Pacific waters shifts atmospheric circulation patterns worldwide, bringing heavy rains to typically dry regions, droughts to usually wet areas, and altering storm tracks in ways that can create extreme weather events thousands of miles from the original oceanic temperature changes. This demonstrates that our planet's weather system operates as a single, integrated entity, where local changes can have global consequences. The role of geography in shaping extreme weather reveals how Earth's solid surface interacts with its fluid atmosphere to create the regional climate patterns that define different parts of our planet. Mountain ranges create orographic lifting that forces air masses upward, cooling them and causing precipitation on windward slopes, while creating rain shadows on leeward sides. Coastal areas experience the moderating influence of large bodies of water, which absorb and release heat slowly compared to land surfaces, creating more stable temperatures, but also providing the energy and moisture that can fuel tropical cyclones. Urban areas demonstrate how human modifications to the landscape can create their own unique weather patterns and extreme events. The urban heat island effect, where cities become significantly warmer than surrounding rural areas, can trigger thunderstorms, modify precipitation patterns, and create localized wind systems. This shows that weather systems are responsive to surface conditions and can adapt to changes in their environment, whether those changes are natural or human-induced. The formation of weather fronts, those boundaries between different air masses, illustrates the beautiful physics of how the atmosphere handles transitions between contrasting conditions. Cold fronts, warm fronts, and occluded fronts each create their own characteristic weather patterns as different air masses interact, producing everything from gentle, widespread precipitation to violent squall lines with tornadoes and severe thunderstorms. These frontal systems demonstrate the atmosphere's elegant methods for mixing air masses of different temperatures and humidity levels. Atmospheric rivers, those narrow bands of moisture-rich air
that can transport water vapor across ocean basins, show how the atmosphere creates its own transportation network for moving moisture from tropical regions to higher latitudes. When these rivers encounter mountain barriers, they can produce extreme precipitation events that provide crucial water supplies to regions like California, while occasionally creating flooding and other hazardous conditions. This demonstrates how the same atmospheric processes that create problems in the short term often provide essential benefits over longer timescales.
The concept of atmospheric memory reveals how current weather conditions influence future weather patterns through soil moisture, snowpack, sea surface temperatures, and other environmental factors that persist beyond individual weather events. A particularly snowy winter can influence summer temperatures through delayed snowmelt. Drought conditions can create feedback loops that perpetuate dry conditions by reducing evaporation and altering local atmospheric stability. This shows that weather systems have a form of persistence, where past conditions influence future possibilities. Extreme weather events often serve as natural experiments that reveal the underlying principles governing atmospheric behavior. Hurricane eye wall replacement cycles demonstrate how storm systems can reorganize themselves to maintain efficiency and longevity. Tornado families, multiple tornadoes spawned by the same supercell thunderstorm, show how rotating storms can continue producing extreme weather phenomena for hours as they move across landscapes. These events provide windows into the self-organizing principles that allow atmospheric systems to maintain coherent structure, even under extreme conditions. The global circulation patterns that connect local weather to planetary-scale atmospheric dynamics reveal Earth's atmosphere as a heat engine, powered by solar energy and regulated by the planet's rotation and the distribution of land and water. The Hadley cells, Ferrel cells, and polar cells that organize atmospheric circulation work together to distribute thermal energy from the warm equator toward the cooler poles, creating the wind patterns, pressure systems, and temperature gradients that drive all weather phenomena. The resilience of atmospheric systems demonstrates nature's remarkable ability to return to balance after extreme events. Hurricanes, while temporarily disrupting normal circulation patterns, actually serve as thermal regulation mechanisms that transport excess heat from tropical oceans toward higher latitudes. Severe thunderstorms, despite their local intensity, help redistribute moisture and energy vertically through the atmosphere. These extreme events, rather than being atmospheric malfunctions, represent the atmosphere's methods for handling energy imbalances and maintaining the overall stability that makes Earth's climate hospitable to life. Tonight, as you rest peacefully within the protective embrace of human shelter, you exist within this magnificent atmospheric system that operates continuously to regulate Earth's climate, distribute moisture and energy around the globe, and occasionally express itself in the extreme weather phenomena that remind us of the dynamic forces surrounding us always. The gentle air circulation in your room, the stable temperature that keeps you comfortable, and the atmospheric pressure that allows you to breathe easily are all products of the same global atmospheric system that creates both gentle spring breezes and powerful hurricanes. This perspective transforms our understanding of extreme weather from isolated threats to expressions of the natural processes that make life possible on our planet.
The same atmospheric dynamics that can create challenging conditions also distribute fresh water to continents, regulate global temperatures, and maintain the atmospheric composition that sustains all terrestrial life. We are not separate from these systems, but intimately connected to them, sharing in the benefits of atmospheric circulation, while occasionally experiencing its more intense expressions. As you drift toward sleep, carried by the rhythm of your own breathing that connects you directly to the vast atmospheric ocean surrounding our planet, rest in the knowledge that you are part of this magnificent system, protected by it, sustained by it, and forever connected to the cosmic dance of forces that make Earth a dynamic, living world, where extreme weather represents not chaos or destruction, but the full expression of the physical principles that govern our beautiful, complex, and eternally fascinating atmosphere.